Welcome to the deep dive. Today we're getting into something pretty fundamental, comparing unitarity and quantum mechanics with the second axiom of probability. At first glance, they look really similar. Both seem to hammer home the same point. Total probability has to add up to 1, always. But, well, the sources we looked at show there's a really crucial difference underneath. So let's unpack this. Why is one just sort of a static rule and the other this active dynamic law?
Right. And to really get the quantum side, we kind of have to start with the foundation it's built on. Probability theory itself, that really goes back to Andrei Kolmogorov back in 1933. He laid out this, well, mathematical architecture for probability. And his second axiom, the unit measure axiom, is key here. It just states that the probability of something happening, anything within the set of all possibilities, has to be 1. Certainty. It's really a definitional thing, a convention. It sets up the probability space, one specific moment. But crucially, it says nothing about time or how things might change. It's just the setup.
Okay, that makes sense for pure math. No time involved, just definitions. But quantum mechanics is all about, well, things changing, evolving through time, right? You have the state vector. So if that state vector describes the system and it's constantly shifting, how do we make sure it still plays by the probability rules? What keeps that total probability locked at 1?
That's exactly the dynamic problem QM has to solve. The quantum state, whatever it's doing, it must always respect those basic Kolmogorov rules. We use the Born rule, that's the bridge connecting the quantum state, the cavalier, to actual measurable probabilities.
Yeah.
So we start with a state that's properly normalized, meaning its total probability is 1. We absolutely need a physical law to guarantee it stays normalized as time passes. You can't just drift to 0.99 or 1.01. That would break everything.
Yeah.
And that physical law is unitarity. It dictates how the quantum state evolves. The time evolution operator, the U, has to be unitary. Mathematically, that means 1 dagger U always fill up. What that does physically is it forces the length, the norm of that state vector, to stay exactly the same over time. Perfect conservation. So unitarity is the active mechanism ensuring probability is conserved dynamically.
Okay. So it's the difference between defining the rules of the game beforehand, like Kolmogorov did, and the rules that dictate how the pieces actually move during the game, which is unitarity.
Precisely. And unitarity has, well, profound consequences. Because unitary evolution is reversible, it means quantum information, in principle, is never truly lost in a closed system.
It can't just vanish. That's
Yeah.
amazing. So the analogy from the source helps here. Kolmogorov's axiom is like defining the chessboard, its size, shape. It's like static.
Yeah, the fixed arena.
Whereas unitarity is the set of rules for how the pieces move on that board dynamically, keeping the game consistent.
Exactly. And what's really key here is that unitarity isn't just a mathematical convenience like saying 1E1. It's a physical postulate about our universe. It's falsifiable. We believe it's true because, well, violating it seems to lead to impossible things like sending signals faster than light. So it's a real constraint imposed by physics.
Wow. So it's a deep feature of reality, not just math. Okay, so the takeaway for you listening is this. Don't confuse the foundational definition of probability, Kolmogorov's axiom,
Which is static, a prerequisite.
with the physical law. Unitarity, which is the dynamic engine ensuring quantum mechanics, actually obeys that probability definition as things change over time.
Right. Unitarity enforces consistency dynamically.
Makes sense.
And maybe a final thought to chew on. Unitarity is, bedrock for standard quantum mechanics.
Yeah.
But some very advanced theories, especially looking at quantum gravity or the whole cosmos, they sometimes explore relaxing unitarity slightly, maybe to something called isometry. This could allow for evolution that isn't strictly reversible. It might connect to things like the creation of new states as the universe expands, suggesting maybe, just maybe, perfect unitarity is an approximation of something deeper, something potentially non-invertible on the largest scales.
So even our fundamental laws might have exceptions at the edge of everything. Fascinating stuff to think about.